All right, so before I get too many comments in the comments section, someone sent me an email asking about functional groups on the test. They are on the test, but not so much in the sense that you need to be able to identify which functional group is which, but more they're on the test in the sense that you need to be able to figure out what intermolecular forces are present in a molecule based on the functional groups that are present. So yes, it's on there, but in the sense of trying to identify intermolecular forces and connect those intermolecular forces to physical properties. Yeah, but there are also multiple choice questions. The bulk of the free response is actually going to focus more on colligative properties, calculations, things like that, because that's more where I need to see your work. All right, any questions for me this morning? All right, in that case, I've got one other comment. For those of you who have started the test tube material, you're going to find that there is a homework set, two homework sets on WebAssign that ask you to find a value but don't actually give you any data. So one is finding activation barrier, the other is describing the orders, and you need to find the various things associated with the graphical analysis. This data is actually on the course, the website. The reason I give it to you is that I want you to get the practice with actually processing data. Students have a bad habit of doing the kinetic analysis, and to them it's kind of an idea in isolation. It's like, well, I'll just give the numbers and analyze it. Well, those numbers come from somewhere, and what you're going to do in the lab when you do it at home is you're actually going to generate these parameters. But this homework is going to give you the experience of processing the data to actually get the values that you're going to report. So to find the data for those assignments, what you're going to do is go to the course website. Under Lessons, you got the test 2, Chemical Kinetics and Rates of Reactions. And you're going to find two Excel files. One is K versus temperature data. This is for finding the activation barrier. So it says test 2, pre-exponential factors, and EA. That's the homework. And then also concentration versus time. And this is for the test 2, concentrations versus time homework. So when you go to do those homeworks, you're probably not going to be doing those this week. But when you get to it next week, that's where you're going to get the data to do those types of assignments. So we're going to answer the second question. I got one question: where do we find the topics for the oral presentation? So on the course website, if you go to quizzes and assignments, lab assignments, you got oral presentation topic suggestions. Now I've already had enough forensic chemistry, and I've had enough, what was the other one? Food additives. Those two, I've had enough students submit that topic that I really don't want anyone else to pick those topics, but otherwise there's really kind of no saturation on the rest of those topics. Now I do have a question about finding molecular weight given molarity. So conceptually, the way you would approach that problem in any type of problem where you're asked where you're given molarity, this is usually found when you're given the osmotic pressure. It's going to be the same way you did the delta T equals KIM calculations yesterday if you look at those live streams. We have pi equals trim. If you're given pi, temperature, and I, your molarity is just pi over TRI. Your molarity is also equal to the moles of solute over volume of solution. So you can get your moles of solute just by multiplying the volume of solution by your calculated molarity. And then you get the relationship moles of solute times the molecular weight equals the grams of solute. The grams of solute are given to you in the problem for these types of problems. So your molecular weight here is just the grams of solute divided by the moles of solute. So this part here is analogous to what you saw when we did the delta T equals KIM calculations to find molecular weight. It's going to follow the same line of reasoning. Solve for the molarity, use molarity to get moles, and take your given mass and the moles you calculated to figure out the molecular weight. And this is what you can do with the freezing point depression lab that you're doing this week as well. check under WebAssign. See if I actually gave any homeworks like that. So actually you do have a homework assignment that kind of follows that same line of reasoning, so I'll just bring it up. So here you got the osmotic pressure, pi. You got the temperature in C, the Van 't Hoff factor is 1, the volume of the solution is 1 liter, and the mass of the solute is 5. And so you'd have the 201.6 here, this converted to Kelvin, I is 1, R is the 8.314, and your grams of solute is 5, and your volume of solution is 1. Do we always use the rate constant R? That's not a rate constant, that's the ideal gas constant, 8.314. Now for this course, this and the 0.008314 are going to be the two we use. There's fundamental reasons for doing this. So the 8.314 is kilopascals times liters per mole Kelvin. This is actually an SI unit, so System International. It's metric. It actually has like units that we can work with. It's also equal to joules per mole Kelvin. And when we take this 8.314, we're going to see a lot, particularly with subsequent tests, this 0.008314, kilojoules per mole Kelvin, comes a lot up in terms of thermodynamic calculations. So one, we want to work with the 8.314 for the ideal gas constant because it's in SI units. The second is that it's only one constant you had to memorize. So it gives you kPa liters, also gives you joules, which you can easily convert to kilojoules. Now in terms of partial credit on the exams, that's why I require you to submit the work. In terms of the free responses, because multiple choice I can't do much for you, but for the free response, typically what happens is I see a lot of calculator errors or intermediate rounding errors. What I generally tell students, 90% of the credit on the free response is your work. So if you get a wrong answer but everything you have set up is correct, I'm going to give you 90% of the points. The only things I'm going to really ding you for in terms of like 1 or 2 points, significant figures, don't give me like calculator output. And if your answer is off by more than 5%, generally I ding you a point. I'll ding you more if it's obvious that your answer is wrong, like if you give me a negative molecular weight, like you knew that was wrong. But generally speaking, getting the right answer for the free response is only 5 to 10% of the credit. Setting it up is the more important thing. The reality is the real world doesn't operate on exams, so you would have time to go back and check. Particularly if you were a new chemist, you would have someone looking over you anyway. So yeah, you're definitely going to get partial credits on the free response. Though some of you who've already submitted your test, I've graded them. You'll see in the terms of feedback to the student, when you click on your exam, you'll see where I took off points. Suggestions for plugging numbers into large FCC and BCC. Best suggestion is to use Excel, but if you don't want to use Excel, my best suggestion is just enter the number in on your calculator and hit enter. And then put in your calculator, but use the answer, the ANS feature in your calculator to refer back to that number. This way you don't have to worry about retyping it. So particularly for something like Avogadro's number or a number you know is going to show up a lot, that's the easier way to do it. But yeah, that would be my suggestion if you're going to use a calculator. Take your unwieldy number and just make it the output for your previous calculation and then use that output as the input for your formula. So formula for finding the melting point, like on the homework, the melting point for ethanol of a 0.596 solution of sucrose. So to solve that problem, delta T equals KFIM. Now keep in mind, melting and freezing are the same temperature. So it's not like ice melts and freezes at different temperatures. It freezes at 0 degrees C, and the reverse melting is at 0 degrees C. So the molarity here, 0.596. It probably gave you the problem the sucrose was 1.00. And then the KF is going to come from from the tables. So let me bring that up really quick. So for ethanol, it's 1.99. But yeah, you would just plug those numbers in. That would give you delta T, and that would be the change in the melting point or the freezing point. Those are the same number. Any other questions? Okay, so converting. So answer the second. So two questions here. Review finding molarity given weight fraction. And are we going to be asked to solve for T1 or T1? No, that's kind of an exercise in algebra. Particularly on exam, you're going to be asked to solve. You're going to be asked to solve the Clausius-Clapeyron equation, but not for something as difficult as T1 or T2. So that leaves the pressures and the delta H's is fair game. The reason I don't really want you going after the T1, T2, it's more of an exercise in algebra than anything else. If you can solve for the delta H, the P1 and the P2, you kind of had the concept down. I'm not really measuring your ability to do like multiple inversions. Now, in terms of molarity given weight fraction, so let me bring up a homework problem. Looks like I don't give you any homework problems like that. Good for me. So we'll look at one of the packet problems then. So there is a problem in the packets, and I'll share the desktop with you really quick. So we'll look at this one. Let's say you have a mass fraction, 0.100, and this is for a sodium fluoride solution, whose density is 0.996 grams per ml. So if you're given mass fraction and you're asked to find molarity, same process as before, write out the units of what you're given. So mass fraction here is grams of solute per grams of solution. We want molarity. Molarity as units of moles of solute per liter of solution. Since we are given weight fraction, we're going to assume one of whatever's in the denominator. So we're going to assume 1 gram of solution. So now we got our three formulas. Moles of solute times the molecular weight of solute equals the grams of solute. Grams of solution equals the grams of solute plus the grams of solvent. And density of solution is the grams of solution all over the volume of solution. So we assumed we had 1 gram of solution. Because of this assumption, we're going to get that we have 0.100 grams of sodium fluoride, because if we take our 1 gram of solution and multiply by our weight fraction, this will give us the grams of solute. What we need to find in order to figure out the molarity is we need the moles of solute, which is here, and we need the volume of the solution in liters, which is here. So this is actually a pretty straightforward calculation. We know the density of the solution here is 0.996 grams per milliliters. So our volume of solution is just 1 divided by 0.996. You'll need to convert that to liters because right now the density is given to you in grams per milliliter. In order to find the moles of solute, all we got to do is take our grams of solute and divide by the molecular weight of sodium fluoride, NaF, and that will give us moles of solute and the volume of solution. Now again, you're going to kind of use this rule of thumb. Typically, concentrations in terms of molarity and molality are 10 to 100 times larger than the concentrations in weight fractions. This is going to be actually a really concentrated solution. So the solutions are up on the course website. But you can see it works out to be roughly 10 times larger, 2.37 molarity. Molarity and molality should be close to each other. In this case, it's 2.37 versus 2.63. But yeah, that's how you work that problem. You're welcome, Julie. As most of you probably saw in my professor review, the homeworks and the packets are substantially harder than the test is going to be. My attitude is you have all the time in the world to do the homework. You only have finite time to do the test. So if you can do the homeworks and you can do the test, you can most definitely pass the test. So if you can do the homeworks and you can do the packets online, you're most certainly fine for the test. Mass fraction was sometimes referred to as weight fraction, and what's the other weird one? It's weight fraction, mass fraction, and weight percent will sometimes show up. There are lots of different little iterations of it. Mass fraction is the correct way to do it. Weight fraction is more of a colloquialism. It's just kind of a shorthand for mass fraction because weight and mass are not necessarily the same thing, although weight fractions end up being the exact same thing as mass fractions because it's just a constant. But your purists would say you would have to say it's the mass fraction because we are working with moles and mass directly comes from moles. Weight depends on where you are in the universe. I will still drop into weight fraction every now and then. That's just the chemical engineering background. They prefer weight fractions because they're a more traditionally English-based unit system. But they are the same statements. Yeah, and I hate the percentage because it throws students off. So, like, when you do a percentage, you have to multiply by 100, but when you come back out, you have to remember to divide by 100. And I get why we do this. Just intrinsically, as people, we like numbers 0 to 100. It's more intuitive to us. But again, why create extra work for yourself down the road? Just give the mass fraction or the weight fraction. If you really want to do percentages, you can do it. But again, you just have to remember when you take the percentages, you have to divide by 100 again to get back to what the actual fraction is. Work smarter, not harder. Yeah, you're very welcome, Tarsha. Like, part of what we have to do for this first test is kind of get everyone to the same page too. So this is why I personally tend to, and most faculty tend to kind of make this first test on IMFs and much more plug and chug problems, and so we can address other things like, who taught you Chem 1, how long ago did you take Chem 1, and we'll start. You'll see with the new discussion board, I think it's already up, about reactions. That's when we start covering things that you definitely would not have seen in Chem 1. Yeah, the one about reaction mechanisms is up today. Other questions? I'm assuming a lot of people are taking the exam this morning because I've already graded about 6 or 7. Usually with exams, I'm going to try to grade them within one business day. I mean, I do kind of want my weekend off, but yeah, usually within one business day, you'll get feedback and you'll know it's graded because you'll see a grade on your work, that 1 out of 1. This is the easiest exam you're going to take this semester, so like, please do well on it. I think the worst you take is test 3 in the final. And test 3 is the first time that it really kind of gets abstract. And while there are lots of right ways to do it, if you don't know what you're doing, you're not going to succeed. But we'll get to that. Also, I've received emails from a few students asking, in terms of the pace of this class, I like to get this material out of the way first. This, I think, is the easiest test and give room for the more complicated materials like equilibrium, thermodynamics, acid-base chemistry, and electrochemistry. You've already paid for the course. Stick it out until withdrawal date. I think that's June 18th is when you can still withdraw without penalty. If you can, go ahead and take the third test before that 18th date and see what you get and make the decision from there. You paid for it, you might as well get the experience. Also, you're going to kind of notice that we're going to have a tone shift for test 2. Right now, this is very much formulas, plug and chug. Reaction kinetics it's very much we don't take anything for granted. We actually explain where everything comes from with reaction kinetics. This test is a lot more just kind of take my word for it, this is the formula. Equilibrium is going to kind of follow the same thing, that it's a lot less take my word for it and more this is how we do it, there's an explanation as to why. So yeah, if you're in the course, you're like, man, we're going fast. Well, yeah, one, it's a summer course. But two, just kind of see how test 2 and test 3 play out for you. And if by that point you're like, oh, it's just not working out, there's a whole reason I try to put that third test before the withdrawal date, is that I want you to be able to sit back and say, okay, this is just challenging, but at least I've learned something. And so when you come to the next, when you take the course again, you had exposure to it, you've got any of my resources that you downloaded, and you're going to either take me again or you're going to take someone else. But again, like, the goal here is to help you out. I want you to have time to figure out if the course is going to work out for you. That's not a decision you need to make in the first week. That's a decision you need to make in the next 2 or 3 weeks. Any other questions? Y'all are rather quiet out there. So I'll give you all about another 3 or 4 minutes, and if no one's got any questions, we'll just end the live stream for today. Next live stream will be Monday. I think it's 12:30 to 1:30 to 2:30. It's on the course website, but same times Mondays and Wednesdays, sometimes Tuesdays and Thursdays. Next week you need to solidly be into the chemical kinetics stuff. I intentionally gave you the problem this week for today, and the reason, and intentionally I'm not going to be grading it or not doing attendance until Monday. Reaction intermediates, catalysts, and deriving rate laws are straightforward, but they do require a little bit of reading when you see them, but they do come from somewhere. Monday, please come with your questions about reaction kinetics. I love catalysis. I did a lot of thesis research on catalysis and reaction kinetics. So this is a great field. What you're going to learn about reaction kinetics is actually like taught. What you're learning now is actually in the beginning of almost all kinetics books. So most kinetics books assume that if you don't know what we're learning right now, you're not going to succeed in the course. So yeah, this is not something that's kind of like you're never going to see it again. It actually shows up a lot in higher division courses. Yields and limiting reagents, or deeper. Yields and limiting reagents are considered a chemistry 1 concept, so we're not going to really talk about yields and limiting reagents. It's kind of assumed you already know how to deal with those. More, we're going to be talking about mechanisms and proving reaction orders. So a yield and a limiting reagent is more what the reaction does when it's done. We're more concerned about what happens between when you start the reaction and when it completes. And that's where the field of reaction kinetics comes from, is that it says that, okay, a reaction doesn't occur instantaneously, it has to occur over time. So what does concentration look like versus time? So again, yields in living reagents, we're going to kind of assume that you already know this. It's more figuring out what reaction intermediates are, what catalysts are, what the order of the reaction is, how the rate of reaction changes based on concentrations. Sometimes it does, sometimes it doesn't. And giving you a foundation for when you take a higher division course to understand, we're going to talk about power laws. Power laws are the basis of higher order kinetic models. So the kinetic models describe how concentration changes as a function of time. You're going to learn where those come from, and then in a higher division course, you're going to start learning how to work with more complicated versions of those. But we're going to focus more on orders, activation energies, analyzing kinetic data. The homework for this test is intense. The test itself is not. The reason the test is not intense is that it's kind of a practical thing. You can't process a whole bunch of data in the course of an exam. But if you understand how to process the data, at least this has been my experience with teaching this material, if you understand how to process it, the conclusions you draw make a lot more sense. So when I teach this, I tend to emphasize a lot more on data analysis, data processing, and then when I give you the pre-processed data, it's a lot easier to understand. It's not like you're just saying, oh, well, this is just a conclusion, but you don't know why. You fundamentally understand why an order is 0, 1, or 2, or why it can be fractional. We can definitely go over yields and living reagents if you want. Usually when I teach this course seated, this is the warm-up problem for the day after the exam, where we talk about calculate the yield in living reagent, just to make sure people understand how to convert between reactants and products. The big thing is that not a lot of students are taught what's called extensive reaction or reaction coefficients. It can put you at a disadvantage if you don't know what those terms mean. We are going to cover them, so I do teach it as if you've never had it before, but they greatly simplify understanding how reactions work. So, problem I like to give for the refresher. We have 1 gram of H2 and 1 gram of O2. And the reaction is 2H2 gas plus O2 gas goes to 2H2O gas. The question is, what's the limiting reagent? And what's the yield? Specifically, what's the theoretical yield? The actual yield depends on actually running the experiment. So if you have 1 gram of H2, 1 gram of O2, the question is, how far does it go? And so the first thing is to make sure, do you understand when this is a limiting reagent problem? And the tip-off that it's a limiting reagent problem is that you're given both concentrations of the reactants. So you're not told one is in excess. Because when we say we're in excess, we mean that we've got more than enough of it. So if you have 1 gram of H2, 1 gram of O2, the question is, who runs out first? And there are 3 ways to do this, to figure out who runs out first. In all cases, you have to convert to moles first, because the thing about grams is they don't tell me how many atoms or molecules are reacting. This tells you how many atoms or molecules are reacting. So if we have 1 gram H2, 1 gram of O2, we've got 2 grams for every mole of H2. For the mole, we got 32.0 grams of O2. So let me bring up Excel. So with hydrogen, this is easy. So you have 0.50 moles of H2. And for oxygen, you have 0.0313 moles of O2. Question is, who's the limiting reagent? Students go, oh, it's oxygen, it's less. No, you have done the problem wrong. You are correct, oxygen is the limiting reagent, but you are correct for the wrong reasons. The thing is that you're not comparing them one-to-one right now. So in order to automatically say, well, this runs out because it's smaller, that presupposes that they're reacting on a one-to-one basis. They're not in a one-to-one ratio, it's a 1-to-2 ratio. So it would be like if you're trying to make a bicycle. So you've got frames and wheels. If you've got 50 wheels and 50 frames, you're going to only be able to make 25 bikes. Not because you want to run out of frames, but because you run out of wheels because you consume them twice as quickly. Same thing's true of this. This happens to be a problem where the smaller number of moles works out, but that isn't always true, and particularly with my Chem 1 courses, I like to cook the numbers so the moles are roughly the same. So when students try to do the trick of going, well, I'll just go with the small number of moles, they end up getting the prompt wrong. What you have to do with the moles, you've got three options. Option one is you can convert to a yield of product. So we can convert the moles of H2 to moles of H2O, and we can convert the moles of O2 to moles of H2O. This is okay if you've only got one product, and that's all you're being asked for is to calculate a yield. To do this, you're going to use what are called the reaction coefficients. So the reaction coefficients are the numbers out here in front of the molecule, and we represent them with the Greek letter nu, I. So it's always the coefficient of what you want to convert to divided by the coefficient of what you're converting from. So if we have moles of H2, we're converting from that. So for every 2 moles of H2, we produce 2 moles of H2O. For oxygen, for every 1 mole of O2, we produce 2 moles of H2O. And when we work it out, this will produce 0.5 moles of H2 or H2O, and this will produce 0.0626 moles of H2O. So the smaller yield indicates the limiting reagent. So when we work it out, this ends up being limiting reagent because it produces the least amount of H2O. That is one way to do it. Another way to do it is we can convert from moles of one to moles of the other. So if we have 0.5 moles of H2, for every 2 moles of H2, we need 1 mole of O2. So in order to react away 0.5 moles of H2, we need 0.250 moles of O2. Well, we don't have that many. So this has to be the limiting reagent because we need more of this to react the hydrogen than we have produced. If this number ended up being smaller than moles of O2, we know hydrogen is the limiting reagent because we have more than enough O2. Now, some teachers do teach this. I've seen increasingly rare and rare. That is a way to do it. The third way, which is the way you're going to get more comfortable with in this class, is just divide by the reaction coefficients. So 0.5 divided by 2 is 0.250. 0.0313 divided by 1, 0.313. These are unitless numbers that are referred to as the extents of reaction. So if hydrogen were to run to completion, the extent of reaction would be 0.25. If oxygen were to run to completion, the extent of reaction would be 0.0313. The reason we want to work with extent of reaction, so our extent of reaction is represented by the variable x. If we want to know moles of any species in this reaction, we just take the extent of reaction and multiply it by the reaction coefficient. So if we want to know, if we knew the extent of reaction here was 0.0313, and we want to know how many moles of hydrogen were reacted, the moles of hydrogen reacted, just that extent of reaction times the coefficient on hydrogen, which is 2. So it would tell us that 0.0626 moles of H2 were reacted. If we want to know moles of H2O, the x times 2, so we'd have 0.0626 moles of H2O produced. So the power of the extent of reaction is that once you know it, converting to everything else in the equation is really just a matter of taking x and multiplying it by the coefficients. Now, the way we think about extent of reaction is the reaction goes a certain distance, so that's why it's called the extent of reaction. How far did it go? Well, how far it goes, if you move from one end of a room to another, We can measure that in a whole bunch of different ways. We can measure it in feet, meters, centimeters, hectares, whatever you want to measure it in. But that distance doesn't change. And that's what extent of reaction says, that the reaction went a distance. Now, if we measure that distance in terms of moles of hydrogen, moles of O2, and moles of H2O, we're going to get different numbers because those are different distances, or they're different units. But ultimately, the reaction goes to a point and stops, and it stops at the same point for everything. Now, the other reason we're going to work with the extent of reaction is that, particularly when it comes to equilibrium, this relationship, moles equals extent of reaction times reaction coefficient, makes it really easy to figure out how much of each reactant and each product was reacted or produced. So, I know that was a lot, but the big picture here, to find limiting reagents, absolutely first you have to be in moles, because moles actually compares atoms to atoms, molecules to molecules. To find the limiting reagent, 3 options. Predict a yield. To predict a yield, take the moles of whatever you're working with, and it's the coefficient of what you want to convert to divided by the coefficient of where you're coming from. Second option, convert to moles of something else. I don't advocate it, but some instructors still teach it. The third that you're going to get more used to is extent of reaction. Take the moles, divide by the reaction coefficient, and the smaller extent of reaction is represents the limiting reagent. To figure out the yield, you can take the moles of the limiting reagent and convert to moles of the products, or you can take your extent of reaction that you calculated and just multiply by the coefficient of whatever product you're interested in, and that will give you your yields. But that's about, 2 weeks worth of a regular semester's summary on how to figure out like yields and limiting reagents. Also, I have other videos. I teach Chem 1 as well. So even though the videos I supply on the website are more specific for Chem 2, if you go to my channel, I actually have playlists for Chem 1 as well. And there's definitely a playlist on how to do reactions, molarity, mass to moles, moles to numbers, back and forth. And I think there's also a few work problems in there as well. So if you ever need something back from Chem 1, again, I tend to keep the course website focused to Chem 2, but definitely on my channel, there's a lot of videos. I have a whole video series for Chem 1 as well. And that might be a resource you might want to consider checking out. Once I got it up. See if I can find you that YouTube playlist. So I'll put this there for anyone who hasn't seen reactions in a long time. This is my playlist from Chem 1. But there's definitely videos on here on how to do limiting reagents and how to do ice tables, which is how I teach. It's a concept that I introduced when I teach Chem 1. But definitely something we're going to work with a lot this semester. There's a lot of video on reaction kinetics. Yeah, you're very welcome. Again, we're not going to focus so much on yield-limiting reagents, so if you don't know how to find a yield-limiting reagent, it's not a good thing, but it's not the end of the world if you don't remember how to do them. But I would definitely start looking at this concept of extended reaction. It is incredibly powerful, and it's one of those things that when we start applying it, it simplifies life so much. Again, it's just describing how far a reaction went without specifying whether it's talking about a particular reactant or product. And we can easily convert that to moles of a given reactant or a given product just by multiplying by what's in the reaction. And with rate laws, we typically derive it based on extended reaction, and then we just multiply the rate law by the reaction coefficient for whatever we're interested in. So we have an extended reaction rate law, and then we just convert that rate law to moles, whatever we want to, by multiplying by a constant. Yeah. You're gonna see this with rates. It's a lot easier if you work in terms of extended reaction. Oh, the other part. Never mind what I was gonna say. The other thing is that chemical engineers really have to emphasize how to do, because I have degrees in both. So chemical engineers really have to understand how to do like reactor modeling, but they have to use a lot of calculus. And if you work with extended reactions, it always gives you a solvable equation. I mean, it may be a nightmare, but it is solvable. This isn't true if you try to work in terms of like individual concentrations of given things. But again, we'll talk about that more next week. Man, week after next, you got a really intense discussion board. Alright, I see many people still out there. Looks like there's 2 other people still out there. I got any questions for me? Alright, so next week, solidly, we're going to be into reaction kinetics. Again, I love this topic. I think it's fascinating, and it's one of the few that we can really explain a lot of what's going on. There's not a lot of hand-waving. I feel like there is with, like, the delta T equals KIM. I mean, it's a formula, but where does it come from? Where do those numbers come from? There's a lot less assumptions built into reaction kinetics. There's a lot more to dig into, and for me, it's nice to know that what I'm teaching you actually applies in higher division courses, and you'll definitely come back to this material. So, again, enjoy your weekends. For those of you who are taking the test, you got through till tomorrow night at midnight. Now, practically, you have until 10 p.m. No, later than that. 10:30-ish is when it's going to cut you off. So, a thing to keep in mind with Blackboard, this is a timed exam. Blackboard is not going to let you start the exam if you have less time between you and the due date than the exam is supposed to have. So it's a 75-minute exam. Excuse me. If you've got less than 75 minutes to take it before the due date, it's not going to let you start. So don't wait until like 10:45 tomorrow night. Go ahead and get it out of the way. Probably not going to grade any exams this weekend, so wait until about Monday about noon to check your grades. But I do try to get them to you pretty quick so that you do have time to go over them. I make mistakes in grading, so please go through. What I have noticed grading these exams is that Blackboard did not save some of the answers I put into some of these questions. So if you're curious how you got it right and it's really far away from your answer, it's because Blackboard didn't save the answer I put into it. But again, this is why I'm grading them by hand. So again, go through your exams. I make mistakes. Let me know if you've got any questions. I typically only give you about a week to contend your grades. The big reason for this is at the end of this semester, I have a lot of people coming back and say, well, on test one, I felt like I could have gotten a couple points back. You need to be looking at your exams now. So you have a week from when, you basically have next week to look over your exams. Let me know if you've got any questions, if you think there's any points where you should be getting points back. And then after that, we're not going to be looking at any revisions. But again, contact me if you've got any questions. Otherwise, I will see you all Monday. So thanks for showing up.